a system of irrigation lines that can be wrapped around a spool and deployed by a helicopter at a mine site. It hasn't been done before. The team has done a good job on this project, keeping an open mind to deliver a more sustainable and efficient system to Freeport-McMoRan.
Hi everyone, I'm Emiliano Morales and I'm an industrial engineer.
My name is Lemia Saleh and I'm the aerospace engineer.
Hi, my name is Lucas Schweers and I'm one of our 2 mechanical engineers.
I'm Annie Wilson and I'm majoring in engineering management.
Hi, I'm Blaze Wilson and I'm a material science engineer.
My name is Abdullah and I'm studying industrial engineering.
So slope leaching is a process that Freeport-McMoRan uses to extract copper each year by making use of low-grade material that can be processed through traditional methods. A sulfuric acid solution is spread over the hillside, dissolving the copper as it flows downward. The enriched solution is then collected, allowing the mine to maximize copper recovery from otherwise unusable ore. So the team has been tasked with the role of creating designs for both a drip line harness and a spooling system for Freeport. Although we aren't creating a full-scale model, we will deliver a final report that includes designs, an operating manual, and verification procedures that will allow Freeport to have a sustainable and lasting solution that will optimize the future of slope leaching.
The team at Morenci currently uses a process of deploying a system of irrigation lines with a helicopter. The system consists of drip lines running vertically, which are attached to HDPE pipes, which run horizontally every 150 feet, secured by duct tape and zip ties to provide support during flight. The assembly process of building these is Freeport's limiting factor in this entire operation. They need the manpower to unroll 1,000 feet of irrigation line at a time. They need people out in the field to strap horizontal crossbars to the system of drip lines and zip tie and duct tape everything together. It's tedious and it takes up a lot of valuable time and space on the mine site that they won't always have in the future. And that's where we come in.
We then worked with our sponsor and realized that we would need to design a custom spool system to not only transport the drip line harness, but would also allow the harness to be unrolled off of it by the helicopter. This was something that we in Freeport were particularly passionate about having, as this would offer a complete solution to Freeport in their slope leaching process.
Now to talk about our system requirements, we have separated them into 3 sections: the design requirements, life cycle requirements, deployment requirements, and finally our safety requirements. Some requirements to highlight are requirement 4.1.3, which talks about our weight requirement for our harness, which should be in between 500 to 750 pounds. To prove this requirement, we performed some analysis to determine that the weight would fall under the range. Requirement 4.1.4, which talks about the drip lines not being affected by any changes we make, and we performed some testing to show that that requirement is passed. Requirement 4.1.5 talks about the design spool shall support the weight of the harness, and we performed some analysis to show this requirement is met. And requirement 4.2.2 talks about how the spool needs to not deform, and again we performed some analysis to show that this requirement is passed. For the TBDs, the team will provide instructions on how the people at Freeport shall test this requirements, since in order to test them we need the full-scale model.
Since we won't be building and delivering a full-scale model to Freeport, we realized that it would be crucial to design prototypes to ensure that our design could work on a small scale. Here are some of the physical models that we created to both visualize and demonstrate that our designs could be brought to life and function properly in a scaled-down model.
So these are the different tests we did using the Instron machine on the different sections of irrigation line. We had some sections that were just pure irrigation line and some sections that had a pressure regulator. That's the yellow guy. The main idea here was that we put it in the machine and then we test it past a limit of tolerance, essentially past the reasonable load that we're expecting to see when the system is put into action and being carried by the helicopter. We tested this at about 80 pounds, which is more than each line would have to individually carry. So here are the force and displacement plots. The main takeaway here is that there isn't any sharp change. This is indicative that the line itself isn't failing when it's inside the Instron machine. This is our FEA analysis. We based it on all the models we used with the blueprints, so it's accurate to what we would be seeing and deployed in the mines. As we can see, there aren't any significant points of concern. I would like to draw attention to our FEA analysis of the strain. If you take a look at the plot on the little right side, You can see that the warmer colors indicate higher amounts of strain. We saw a lot of this in the arbor holes. But most importantly, if we compare this to our fatigue life cycle chart here with ASTM A36 steel, we can see that it's actually below the limit where a high number of cycles would cause this metal to fracture. We can safely predict that the metal isn't going to fail after a large number of repeated uses. We're likely going to see these changes in amplitude of stress whilst the actual spool is rotating and force is acting on it in one direction and then the exact opposite direction as the spool spins around to the other side.
For our first important analysis, we have the total drip line harness weight analysis to make sure the optimized design is within the weight margins as per one of our system requirements. This method is involving known weights and includes the entire system, including the drip lines, the ropes, the header bar, and the weight bar. The values used in this analysis were mostly provided to us by Freeport-McMoRan, but the one that involved some sort of calculation was the total mesh weight required per harness, which turned out to be 70 pounds, give or take about 4 pounds, based on the fact that one harness might need 8 or 9 rolls. Also, that weight pipe at the very bottom is not fixed, meaning that 10 pounds could be added or removed as deemed necessary. Overall, the total drip line system would weigh 712 pounds, plus or minus about 14 pounds, which is within the margin required. The next type of analysis we performed was a drag analysis on the drag force created by the added surface area of the mesh. This is to make sure that the rigidity of the optimized design is not compromised by that added force causing this harness to fly through the air, as per requirement 4.1.4. This analysis does have some constraints, however, including that it does not consider drag by other subsystems and assumes the helicopter cruises at an average speed of 35 miles per hour. This is, however, an educated assumption given the significant payload the helicopter is carrying, meaning it is unlikely to be more than 35 miles per hour. For this analysis, the aerodynamic equation is used, including the density at the altitude of the helicopter, and this also takes into account the length of the system, the velocity, the surface area of the mesh, which is obtained from knowing the total area of holes in the orange fence and subtracting that from the area of the fence. The drag coefficient here was obtained from known data for the coefficient of drag of a flat surface. The total drag force was calculated to be about 2,300 pounds, and this number might seem big but should not be a problem due to many reasons. One, the harness is actually able to counteract the moment caused by the drag using its weight of 712 pounds. Two, the thrust caused by the helicopter also counteracts that drag moment. And three, and this is just to be safe, there are simple solutions to minimize the drag, including flying at higher altitudes and decreasing the speed.
All of the tests and analysis done on this project were performed to prove one thing, that we created a design that will work for our customer. After a year's worth of learning, working, and pushing through challenges, we have delivered a design that exceeds our customers' needs. Thank you for watching this video.